For our lesson today, we're going to look at graphing polynomials. The first part of this should be a lot of review of what we've already talked about with polynomials. So when we have a polynomial function, some of our key components deal with that leading term, that first term, because we see our leading coefficient, our degree of the function, and the regular coefficients will help tell us some things about how I find the zeros. The last term is our constant term, and if it's in standard form like this, we know that's the Y-intercept. So the leading term has the greatest influence on the end behavior of a function. We've talked about what the end behavior is, but just as a review of this, the degree and the leading coefficient will tell if it's going to be something like a down-up behavior. So this was a down-up. That's when it was an odd degree, but A was positive, so it went down on the left and up on the right. If it was an odd degree, like a cubic function, but A is negative, it's been reflected, that's where it's an up-down behavior. So it's going up on the left and down on the right. An even degree, just like a quadratic or a fourth degree, sixth degree, those are going to be up behaviors when A is positive, but if A was negative, then we have a down behavior. We'll look at what that does to our graph here in a second. We can sketch a graph of the polynomial if we know the y-intercept, the zeros, and the multiplicities of the zeros. So just to review, what's a zero? A zero is an x-intercept where it crosses the x-axis of the graph. They are also known as roots, but zeros are not the same thing as factors. They are correlated. They tell us some things about each other. So if I know that c is a zero, then x minus c is the factor. So a factor is something that makes up the function in factored form. Here we have something that's in factored form, and everything is being multiplied together. That's what tells us this is in factored form. And if I want to find the zeros of the function, we set each factor equal to 0 using our zero product property. So each factor equal to 0. Now I don't have to set this -5 equal to 0 because that's just a constant factor. That's our vertical stretch or vertical shrink, depending on what the value is. But x minus 3 equals 0, x plus 4 equals 0, and 2x minus 1 equals 0. And we just solve them from there. So x equals 3, x equals -4, and 2x equals +1, so x equals 1/2. Now we've gone back and forth between zeros and factors already. So we should be able to just write our zeros out. Sometimes we write them in order, but they would be those 3 zeros. So if we know how many zeros there are, that also tells us something about the type of function we're working with. So this is a cubic function because there are 3 zeros. So let's review what a multiplicity is. Multiplicity will tell us how the graph behaves at that 0. So here I have a graph that's going through x equals 3, and it's going straight through the graph. That means that has a multiplicity of 1. This went straight through 2, so it's also a multiplicity of 1. Now if we had an odd multiplicity, but bigger than 1, so something like if you did x minus c to the 3rd power, whatever that 0 is, it's going to bend or wiggle, I like to say it wiggles, through the graph, or through the axis. If it was even, something like x minus c squared, that's where it bounces off the x-axis. All right, now the last thing we need is the y-intercept. So we'll review that as well. This is when x is equal to 0. We did say that if it was in standard form, like this, the y-intercept is just that constant term because every x would be 0 except for that constant term. But if it's not in standard form, we still need a way to find the y-intercept. So I find f of 0. So negative 1/4 times 0 minus 3 times 0 plus 2 squared. You can put that in your calculator, or you can work it out algebraically, either one. So 0 plus 2 is 2 squared is 4. And you just work that part out. We'd end up getting negative 1/4 times negative 12, which is a positive 3. You can get that either by using the calculator or just do it out by hand. But 0,3 is my y-intercept. So if we know all those things, then we can graph or at least sketch a graph of the function. All right, that means that we have here a function that we need the leading term because it's not in standard form. We talked a little bit about how to do that, but just to review, let me rewrite the function down here. All right, our leading term is going to come from if I had multiplied this all the way out. So I would have done x minus 3 times x plus 2 times x plus 2 since it's a squared. We can only multiply two things at a time, so maybe I would have multiplied this and gotten x squared plus 4x plus 4. And then we would have distributed the x minus 3. So this would give us x cubed. X times 4x would be 4x squared. X times positive 4 is 4x. Then we distribute our negative 3, so negative 3x squared. Negative 3 times 4 is negative 12x. And then negative 12. I'm going to clean that up before I distribute the negative 1/4, so that's x cubed plus, we have a 4x squared and a negative 3, so that's just 1x squared. 4x minus 12x is negative 8x, and then minus 12. The last thing we would do is distribute that negative 1/4, so it would be negative 1/4 x cubed negative 1/4 x squared plus 2x plus 3. Now this is not an expectation that we have to multiply this out into standard form every time, but we do need a way to determine what the leading term is without having to multiply this all the way. So we do that just by paying attention to the degrees of each factor. So this is going to be a negative 1/4 times an x in that first factor times an x squared in the second factor. So if I had multiplied that together, that's the negative 1/4 x cubed. And all I'm looking for is that leading coefficient or leading term. So I don't need this entire standard form, but that is what tells us we have a cubic function, so it's a degree 3. The negative 1/4 will reveal that we had something that's going to go up, down now. Now that's going to be a little bit harder for us to remember because you have to think about all the different types of graphs, but an x cubed graph or any kind of odd degree had opposite behavior. So it would normally start out down, up, but since it was reflected when a is less than 0, now it's going to go up on the left and down on the right. So that's how I got that this was an up-down graph. All right, our zeros come from each factor. So I see in that x minus 3, I'm going to have a 0 at 3 with a multiplicity of 1, and another one at negative 2 with a multiplicity of 2. Our last one is our y-intercept, which we already found, 0, 3. And we just try to sketch this out. So if I sketch the zeros first, I'm going to go to -2 and put a point, +3, put a point, and then I can graph the y-intercept. So 0, 3, 1, 2, 3. All right, now we know that it had an up-down end behavior. So if you do this, I would recommend doing it in pencil, just because it's going to possibly give us some mistakes. But I know at this -2, it's going to bounce. It bounces off the axis because it had a multiplicity of 2, and it's going to go through, straight through the point at 3. We had up, down in behavior. That gives us a little bit of an idea of where this is going to go. So we need to be coming from this area and go bounce off at -2. So there's our left side, and we're going to go through that y-intercept. So let's go through here. But eventually, it's got to come back down because we need to go through that point. So I'm going to go back down and go through there. There's a rough sketch of what our graph looks like. Now, one thing to make sure is that we don't really know what the other points are on the graph. I also don't know exactly where that turning point was. I just know that it should go through 0, 3. So there's no way for me to determine what the maximums or minimums are at this point. Once you get to Calculus 1, you get to learn some cool things about how do I find out more information of a polynomial function like that. All right, so look at example 2. We have -2 times x plus 3 squared or cubed and 2x plus 1 squared. So that leading term, we're going to find that first. -2 times, here we have just an x, but it's cubed. And now there's a 2x squared. All right, with the 2x, let's pay attention because that's going to be 2 times x cubed times 4x squared. This squared is multiplying 2x times 2x. All right, and then that's a total of -8x to the fifth degree function with a value of -8. Since a is negative, that tells us that the graph reflected. So an odd degree would typically go down on the left and up on the right. It has been reflected, so a is less than 0, so now it's going to go up on the left and down on the right. So it's an up, down behavior. Our y-intercept, well, that takes a little bit of algebra. So let's find f of 0. -2 times 0 plus 3 cubed, 2 times 0 plus 1 squared. So -2 times, 3 cubed is 27. 2 times 0 is just 0, and 0 plus 1 is 1. So 1 squared is 1. And then we multiply that out. So 2 times 27 is 54. So again, -54. All right. That tells us automatically that I'm going to need a scale for this axis because it's going to, there's no way I'm going to get down to -54 if I count by ones. And the zeros, the multiplicities, let's see, I'm going to have, let's write it out just one more time to do this properly. -2 times x plus 3 cubed, 2x plus 1 squared. If I set each factor equal to 0, hopefully by now you're seeing some patterns that are happening, but I'm going to have x equals -3 and 2x equals -1, so x equals -1/2. Those are the zeros, so I would have a 0 at x equals -3 with a multiplicity of 3. and another one at x equals -1/2 with a multiplicity of 2. Okay, so let's figure out what scale do we need. I can count by ones on my x's because I just need to get to -3 and -1/2. But my y's have to go all the way down to -54. So maybe I just count by tens. So that'll be -10, -20, -30, -40, -50, -60, 80, 90, -100. And when it's really small like this, what you could do is skip count. So you could do every other one. That maybe would give you a little bit more space. But my x's can count by ones. So I could still put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's what I'm talking about skip counting. You don't need to write every single one in there. But -2, -4, -6. -8, and -10. All right, let's put some of these points in there. So I got -3 and -1/2. We also have to go all the way to 0, -54. So that's somewhere about there. So you can imagine that's going to be pretty steep going on in between these two things right here. Based off this function, we had an up-down behavior, so I'm going to go up on the left, down on the right. We had a multiplicity of 3 here, so this was going to be a bend or a wiggle, and at -1/2, it will bounce. Okay, so if I need to come from this direction on the left, I'm going to go somewhere about there, and I know it needs to bend. So that's going to be where it kind of just wiggles. It doesn't go straight through. It makes that curved pattern. So something like this. But if I keep going down, I'm never going to get to that point. So this means I'm going to need to turn back around at some point and bounce off of that. So it's going to be very steep. So I'm going to go and bounce and then go through this point like this. Now, one thing I could have done is change the x-axis so that I had a little bit more space and spread that out a little bit so I didn't count by every single one. But for purposes of what we have, a general sketch is perfectly fine. All right, examples 2 and 6 here are coming from our lab manual. What I see so far, I can find the x-intercepts. So I'm going to have one at x equals 5, another at x equals 4, and another at x equals -1. All of those are multiplicities of 1. So they're going to go straight through that point. So I'm just going to go ahead and plot those. So -1, +4, 1, 2, 3, 4, +5. And we need a y-intercept. So let's find h of 0. -0 minus 5, 0 minus 4, and 0 plus 1. -5 times -4 times 1. So that would be a +20, but when we multiply it by another negative, makes that -20. I'm going to need a scale again. So maybe we just count by 2s. So that would be a -4. So notice I skipped this time. So that first one's -2, -4, -6, -8. -10, -12. -14, -16, and -20. So I did that so that I would have a little bit more space here, but I know I'm going to have to go through that point. So that means that first mark on the positive y-axis is 2, then 4, 6, 8, 10, 12, 14, 16, 4, 8, 12, 16, and then 20. Perfect. All right, these are counting by ones, so you could put in 2, 4, 6, 8, but you would count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so I've put all those in there, but we just want to now sketch out what we have. Actually, whoops, I need one more thing. Let's find that leading coefficient. So this was a negative times x times x times x. Make this a negative x cubed. X cubes usually would go the same way. We have a lot of these graphs right now. So it usually would go down, up, but a is now negative, so it's reflected. It goes up, down. That tells me where I should be coming from. Up and down on the right. All those had multiplicities of 1, so we're going to go straight through the axis. So I'm going to go through that point, and I got to go pretty steep. I should have made this even more steeper. Oops. And go back up. So I went through 20, negative 20, and back up. Means I need to go through 4 and come back down, hit 6, and then we can go back that way. So you could have made this a little bit prettier and gone like this. This is why I don't use pen for this usually, but I wanted you to be able to see it clearly in the picture. So let's just kind of ignore this weird line. All right, number 6. We can find the zeros. I think that's the easiest part to do if it's already in factored form. So let's do that here. X plus 3 squared. One thing I see students mess up is that they will forget that first factor of negative 3x, and because there's an x there that's going to have a factor, it always will give you just a 0 because it's just an x value there. But then we have our x equals 2, our x equals negative 3, and the multiplicity. So this negative or positive 2 is a multiplicity of 3, the negative 3 is a multiplicity of 2. All right, our y-intercept, if we were doing that, so we'd find c of 0. Negative 3 times 0 times 0 minus 2 cubed times 0 plus 3 squared. Maybe just put that in the calculator, but negative 3 times 0, 0 minus 2 cubed, and 0 plus 3 squared. It comes out as 0. So I've got a y-intercept of 0, 0. We found our x-intercepts here. So there's our y-intercept, 0, 0. At 2, I'm going to actually make this wider. So I'm going to change the scale slightly. So if you can see, I made every other one 1, 2, 3, 4. So really it looks like I'm counting by 1/2. That makes the x-axis a little bit wider for me to work with. But I'm going to have a point at 0, 0 right there, another point at 2, and another point at negative 3. The y-intercept is 0, 0, so I don't need to plot anything else on the y-axis. We do need our leading term. So we find that by multiplying out, but negative 3x times an x cubed, that's going to be a cubed, and then x squared would be negative 3 times x to the 6th power. I'm getting 6 because there's one x here, 3 x's there, and 2 more. So 1, 2, 3, 4, 5, 6. All right. That's an even degree. So even degree functions have the same end behavior. It's up, up, or down, down. Since a is negative, that tells us it's down, down. We can just kind of write that out here on the graph. But we know that both of those should be pointing down. All right, at negative 3, what it does is bounces because it's a multiplicity of 2. So there should be a bounce at negative 3. It should go straight through 0, and it should bend or wiggle through positive 2. So I'm going to come from down below and bounce off the x-axis at negative 3. It's going to have to go back up because I need to go through 0. So I can go down for a little bit, but eventually I need to come back up. And we don't know exactly how far it goes down. We're not worried about it. Then once we go back up, eventually it comes back down because we're going to bend through that positive 2. So I can wiggle or bend. It's not going straight through. Notice you're going to have a little curvature to it. And it goes back down. So there's a general shape of this. Our last one. Okay. It says to be careful when your factors are not in descending order. You can move them around so that they are in descending order, or you can just be very careful with it. Either one is fine. All right. So I need to find out the zeros. I do that the same way we've been doing it. We set each factor equal to 0. So x minus 3 equals 0, 1 minus 2x equals 0, and 4 plus x equals 0. What is talking about descending order is really the degrees of each factor. So notice how this has the constant term first and then the x. This has the constant term first and then the 2x. So this is not technically in descending order of a factor. All right, but we can still work with it. So this same one here, because it's x equals 3, we've been doing that. I would subtract 1 first to get negative 2x equals negative 1. And then divide by negative 2 would give us a positive 1/2. If I subtract 4, I get negative 4. So that's why I said just be careful. You can still find your zeros for that. This negative 4 has a multiplicity of 2, so it should bounce there. If we found our y-intercept, f of 0, negative 1/2 times 0 minus 3 times 1 minus 2 times 0, and then 4 plus 0 squared. And 4 squared, 16. So let's see, 16 times 3 is 48. Half of 48 is going to be negative 24. Whoops, a positive 24 because a negative times a negative. That means that we're going to have to change our y-axis, but that's okay. The last thing we need is that leading coefficient. So let's write that out, 0, 24. We have our zeros here and our multiplicities. So that leading coefficient, or leading term, we're going to multiply negative 1/2 times an x. And then this one, I'm looking at where the x is, so negative 2x. And then this one is an x squared. So if it's not in standard form, then you would just put it, look at it in descending. If it's not in descending order, I mean, you need to look at it carefully so that you can find out that leading term. But either way, we should still get a negative 1/2 times 2, so that's a positive 1. X times x times x times x. So there's 4 x's here. So that's x to the 4th. X to the 4th is an up in behavior. And we can write that on our graph as well. So up, up. Now, if you had wanted to put this in descending order, you could have made this f of x equals -1/2 x minus 3. But this factor would be rewritten as -2x plus 1. So just pay attention to your negative. The 2 was being subtracted. That means it's a -2. The 1 is positive, so we get a plus 1. And then x plus 4, that one's a little bit easier to rearrange, squared. So that's what it would look like if I had put it in descending order. Just pay attention because some of the lab manual questions are out of order like we have here. Let's put in our zeros first. So I've got x values. Since this is a 1/2, I'm going to change the x-axis just like I did the last one. So instead of making this first one a 1, let's make the second one a 1. So every other one gets to be an integer. So I've got that first nice tick mark would actually be a 1/2. There's our point. If I did the negative side, there's -1, -2, -3, -4, -5. So just make sure that if you change the scale, you're consistent the whole way through. So I can't just now start doing by regular 1, 2, 3, 4 on every single line. You have to maintain that scale for the whole x-axis. Same for the y-axis. I need to get all the way down to 0.24 or up to 0.24. So somehow I need to count by something else. We could count by, let's see, 2's would only get me to 20, so maybe 3's. So 3, 6, 9, 12, 15, 18, 21, 24. So 0.24 is a point. And let's see, oh, I didn't do the rest of the zeros. We did 1/2, but +3 was a point and -4 was a point. Okay, we know it's up, up. We've done that part, so it's going to go down this way towards that -4. Once we get to -4, it should bounce off the axis. It's bouncing because it's a multiplicity of 2. Let's go down towards that -4, but bounce straight back up. We're going to go and eventually have to hit through this 24, so let's kind of make our way that way. And since it's going through this 1/2, it's going to have to get steep at some point. All right, at 1/2, it's going through the point. And it goes back through 3. So we saw our up, up behavior. Now, if it's helpful, go ahead and put in, like this is a bounce. This is going through. This is going through. I would maybe do that in pencil so that your graph comes out nicely, but either way, you want to make sure that your scale is correct and you've put in your zeros with the correct multiplicities. All right, go back and try some of these in the lab manual and you can check your answer with the key.